Hi everyone, this is your thank God I'm not a ESPN Sports Center host, physical chemistry instructor Dr. Hopkins. We are going to start our next section of the PChem where we're talking about multi-electron atoms. And so, as I stated in the past when I was talking about hydrogen atom is the last one we can solve because the problem becomes analytically impossible. Okay, and so we're setting this up in terms of just helium. So we take the simplest multi-electron atom. We have a nucleus and two electrons. So the Hamiltonian is the kinetic energy operators of the nucleus and the two electrons. Of course, the nucleus kinetic energy operator we ignore because that's still center of mass motion. It doesn't matter how many electrons we add. The center of mass is still the nucleus. So that's translational. But then we still have the kinetic energy operators of the electrons, and then the potential energy operator between the nucleus and the electrons. So that's very similar to the hydrogen atom. There would be some differences, but it's very similar to that. But the problem arises in the last term, the fourth term, where we have a potential energy representing the interaction between the two electrons. The electrons are too negatively charged, right? And so there would be a repulsion. So if you went back to your physics and you had a repulsion between these two negatively charged particles, the problem is that now our particles are probability, so they're just waves. Okay, so how do you figure out what's the distance? Because there's a distance dependence in Coulombic interaction between two waves. So that's what fundamentally causes this to break down, and we can no longer solve the Hamiltonian analytically. So anyway, so as a physical chemist, what we want to do, since we run into this problem, okay, now we can't calculate it exactly, so we need to come up with a model, or we try to come up with a model. So what we're going to do is we're going to come up with the simplest approximate model and see how close we can get to the energy. All right. So our first attempt is the zeroth order model. And the zeroth order model is, like I said, easiest, but also the most incorrect. All right, so we'll learn that in a little bit. So basically what we're going to do is we're going to say that all electrons are independent. They are occupying orbital wave, hydrogen-like orbital wave functions. We're going to add in the additional nuclear charge, so that may shrink some of them. And then we're just going to sum the total energy. So there's not going to be any kind of cross term. So our one electron energies, we sum them up. That'll be our total energy. So that simplifies it pretty well. And then we're going to end up with a new term. So it turns out when we have multi-electron atoms, we have this new quantum number we have to introduce called spin, or electron spin. And then we will apply the Pauli exclusion principle to assigning electrons to the orbitals. It turns out the spin doesn't, in the zeroth order, doesn't really affect the energy very much. But since spin is an angular momentum, we have orbital angular momentum and and spin angular momentum. So we're going to assume that they are also independent, and we can just add them together. All right. So the zeroth order atom. Let's work through helium first. So each one electron wave function is now going to have a spin orbital. So we have Nl, M sub L, our very familiar quantum numbers from hydrogen atom. And then we're going to add a fourth term in, so that's the spin quantum number, M sub S. And we will address in much more detail the spin quantum number and the Pauli exclusion principle after we finish this kind of quick calculation. And so then we go back to our Hamiltonian for helium. We're ignoring the nuclear because that's translational. And so then we can take the two kinetic and potential energy operators for each of the electrons, and we'll separate them. So this small h1 and small h2 are one electron Hamiltonian. So that's like a hydrogen Hamiltonian with a z equals 2. And then the last term is our electron-electron repulsion potential energy, which in the zeroth order approximation is equal to 0. Okay. And so then we're left with a Hamiltonian or the Schrodinger equation that is H0. So for the zeroth order approximation, we can solve for an eigenvalue and an eigenfunction. It turns out the eigenfunction is just the product of the two one electron eigenfunction, for the electrons in helium. And then our eigenvalue, E0, is just the same. So this is adjusted for, I don't have the quantum number, but it's only a function of the quantum number n. So remember, L and M sub L don't affect the energies of the electrons in hydrogen atom in the 0th order approximation. They also don't affect the energies in any other atom. So anyway, we end up with this. We just multiply it by 2. And we end up with a binding energy of like 10.5, minus 10.5 times 10 to the 6 joules per mole. Now, if we look at the experimental binding energy, it's minus 7.6 times 10 to the minus 6, 10 to the 6, joules per mole. So we're basically getting this. The model is overestimating the energy by about 50%. So we're wrong, okay? Which we knew we would be because this is the easiest, but also the most incorrect. All right. So let's address spin. So spin's a new quantum number. It doesn't have a classical analog at all. We do visualize it as a spinning electron. The reason why that works is that if you spin a charge, you'll get a magnetic field. If you spin in one direction, you'll get a magnetic field. Spin in the opposite direction, you'll get a magnetic field in the opposite direction. So the spin quantum number just explains the fact that electrons will split in a magnetic field. Okay, and so we then have the Pauli exclusion principle, which we use to explain how we put spins in this. We factor spin into our orbital occupation. And this is the general chemistry definition. Was basically stated that we got 2 electrons per orbital, and if we put 2 electrons in the orbital, the spins must be anti-parallel. Okay, and so what do we mean by anti-parallel? We call them up or down. In this case, we're just going to assign them spin quantum numbers. So m sub s is plus 1/2 or minus 1/2. The plus 1/2 we typically refer to as spin up, minus 1/2 as spin down. We are going to use new notation in the class where we call the spin up alpha and the spin down beta. So a more comprehensive reading of the Pauli exclusion principle, it applies to all elementary particles, and I've included both, but the top one is the only one that we really are too worried about. So fermions are elementary particles with half-integral spins. Okay, so all of our subatomic particles, electrons, protons, and neutrons, are considered fermions. Okay, and now a fermion is what we call an indistinguishable particle. So if you're reading in the book, and this is actually in chapter 10, they're indistinguishable particles. We can't put a label on one electron and just follow it around and know that that's that particular electron. Okay, so as it quotes, so the Pauli exclusion principle states that for fermions, the total wave function has to change sign under pairwise permutation of particle labels. So if we labeled this electron 1 and this one 2, and then we switched the labels, what would happen to the wave function? And it would change sign, but it would be an eigenfunction, and that's what's called antisymmetric. Okay. Now, if you're a boson, like an elementary particle that has integral spins, like some nuclei have integral spins. Now, these combinations of fermions can also be botons, but photon is a classic example of a boson. And photons, the total wave function does not change if you switch the labels from 1 and 2. And so those are what are called symmetric. So if we go back to our helium atom has 2 electrons. And so we want to think about how will we add spin into what we already know about orbital functions. And so our possible 2 electron spins are, spin functions are spin up, spin up, spin down, spin down, spin up, spin down, spin down, spin up, right? So we have our alpha, alpha, beta, beta, alpha, beta, beta, alpha. Now, if we do the pairwise permutations, and I'll show you the first one, I show all of them, but you show the first one where you're doing spin up, so we just switch the labels on 2 and 1, and you're left with basically the same eigenfunction, because it doesn't really matter which order you put those alphas in. And so it's an eigenfunction, but it didn't change sign, right? So its eigenvalue is +1, so it's symmetric. Same happens for beta, its eigenfunction, and it's symmetric. But now if we look at the cross terms where we're spin up, spin down, and those are likely to be our anti-parallel, right? So let's look at this. If we did the pairwise permutation on alpha 1, beta 2, we get alpha 2, beta 1. That's not an eigenfunction. You can't rearrange that and come up with alpha 1, beta 2 again. You've switched the labels. And the same is for the other cross term. So what we do is we make linear combinations of those 2 spin functions to account for the fact that it could be the first one spin up or the first one spin down, and it doesn't really matter, and we can't distinguish between the 2 of them. And so the way we do that is we put these linear combinations together, and so we have the sum of both of those terms, and we have the we subtract one from the other, and it doesn't really matter which one you subtract. If we do the pairwise permutation on the one where we're summing them together, now notice the 1 over square root of 2, that's basically a normalization constant. I've included it here for completeness sake, but it's not all that important. It just shows that they're normalized. Anyway, so if we're doing our pairwise permutation, we do alpha, beta, beta, alpha, we will return what I show there, but you'll notice that's just plus the same thing, so we get an eigenfunction of the pairwise. So now our linear combination is an eigenfunction, but it's still symmetric, okay? And then on the last one, where we were subtracting the terms, now we get an eigenfunction, but it's anti-symmetric because the way to relate those two is you would have to put a negative sign there. And if you subtract it, if you pulled a negative out of there, you would return our original wave function, or eigenfunction. So then let's apply this back to our helium atom. So we've done the 0th order approximation for helium. So let's think about what would these wave functions look like. So we had the hydrogen wave functions. They were orbital wave functions, but we did have to add in spin. And so what's the electronic configuration? The ground state for helium has 2 electrons, so we put them in the lowest energy states. It's 1s2 because we have two electrons per orbital, right? That's what we learned in Gen Chem, so this would be good for Gen Chem, right? Now, if we look at this and we said, well, does it actually apply? I mean, does this fit the pairwise permutation for the Pauli exclusion principle? And if we switch the labels on 1 and 2, this is symmetric. Okay, so the orbital function is not anti-symmetric, so that does not describe the situation, or that, excuse me, that's symmetric. So then that means because our total wave function must be anti-symmetric, the spin wave function has to be the anti-symmetric one. Right, so we had we had 4 possibilities on the previous slide. The only one that works with a symmetric orbital function is an anti-symmetric spin function. And so our total wave function for helium would have to be 1s1, 1s2, and then this linear combination of spin up and spin down. And so next time when we will add in, we'll go to a little bit larger numbers of electron atoms. We'll revise the 0th order model and kind of get a little bit closer to figuring out what's the actual energies of these systems.